Okay. Hello, everyone. My name's Kyle. I'm the Vice President of Events here at the Carleton AI Society, and I'm here today with Abdullah for our lecture. So I'll let him get right into it.
Okay. Thank you, Kyle. Hi, everyone. Today we're going to discuss dimensionality reduction, which is one of the basic topics in machine learning and deep learning. First of all, I'd just like to thank our sponsor, CPA Ontario, for their funding, and then I'm just going to dive right into it. So today we're going to start first by defining what is dimensionality reduction, talking about the different methods in the literature, but then we're just going to focus on only two methods. But these are two of the most popular methods, which are principal component analysis, PCA, and linear discriminant analysis, LDA, right? So the first question that we ask ourselves is, if we have a data set, which one is better? Is it better to have more features or less? When is it good to have more features, and when is it bad to have more features? Well, it is good to have more features when these features are complementary, when they're independent, when they provide more information, because then adding more features will always improve the performance of your model because it will reduce the bias error. However, having more features has its own problems as well, because if the features do not carry relevant information, that's not going to be helpful. If the features are noisy, and also the performance of a classifier, if you have less features, could be better than one with more features, especially if you have a very small data set. And also more features also means that the model is going to be a lot more computationally expensive. And the more features you have, you're going to need a lot more samples, because we would like, whenever we do our analysis, we want to have more samples than there are features. So if n is the number of samples and d is the number of features, we would like n to be significantly larger than d. And this is actually called the curse of dimensionality, which is as the dimensionality of the data increases, you're going to need many more samples in order for you to have a good generalization based on your model and to avoid overfitting, right? So why would we want to reduce the dimensionality of a problem? Well, there are multiple advantages that we gain by doing that. The most basic ones is, well, if you have less features, if the dimensionality is lower, then you're going to have the time complexity is going to be reduced because you have less computation. The space complexity is going to be reduced because there are less parameters for the model to learn. Also, simpler models tend to be very robust on small data sets. And when you have less features, it is much easier to interpret your model. It's much easier to have an easy explanation. It is easier to visualize the data, right? So, but before we reduce the dimensionality of the data, we have to talk about our main assumption. Our assumption is this, is that natural data in very high dimensional space actually concentrates close to a lower dimensional manifold. And the best way to explain that is to think of natural images, right? So think of any image that's 100 by 100 pixels, right? With then length is 100 by 100. And each pixel takes 256 different values. So if you think of all the possible images you could generate by just running all the possible values on an image, you end up with a lot of images. However, the natural images that you capture, no matter what's the content of the image, tend to occupy a very small fraction in this very large space of all the possible images. This is why reducing the dimensionality of a data set makes sense, right? And there are two ways to reduce the dimensionality of any data set. And there are simply two categories of methods. The first one is called feature selection, and the other one is feature extraction. Feature selection is simply this. If you have a data set that has D features, you only select a subset of them where you select the best K features, and we will talk about what is the best means, right? However, feature extraction means taking a data set that has dimensionality D and creating a new subset of features that has size K by transforming the original features. So in this talk, we're going to focus on feature extraction, not feature selection. And feature extraction can be divided into two main approaches, linear methods and nonlinear methods, right? So linear methods, when we transform the data, we do a linear transformation. And this includes principal component analysis, linear discriminant analysis, multidimensional scaling. However, there are nonlinear methods, which we can talk about in the future, where when you transform the data, the transformation does not have to be linear. such as local linear embeddings, self-organizing maps, and isomaps, and so on, right? So when we're trying to do a linear feature extraction, what we simply try to do is we'd like to find a good mapping function that takes the data X, this is a data sample, and this is the function that is going to transform the data to reduce dimensionality, and Z is simply the new transformed data. And as you can see, we're going to go from D-dimensional space to K-dimensional space, where K should be smaller than D, right? So a good mapping function is supposed to transform and reduce the dimension of the data while also retaining as much of the original information that was available in the original data, right? And since we're going to focus on linear transformations, we know that function f is going to be linear. And simply, we can interpret it as simply having this transformation matrix W, right? So what we're trying to learn, we're trying to find a good matrix W that transforms data X by reducing its dimensionality to learn Z, where this transformation matrix W is going to preserve as much of the information that is available in X as possible, right? So the mapping function, we're trying to find a mapping function. How do we select? How do we find this good mapping function? Well, to do that, we have to define a criterion or a cost function, an objective function, and we try to either minimize it or maximize it, right? So how do we select W? Now, you notice we're using capital letters here, which means we're showing the entire data set, right? So we have the whole data set X, which has dimensionality D, n, where we have n samples and each one has D features. And this is the new data set we aim to learn, which is the transformed data set, which is Kn, where we have K features. And this is the matrix that we will actually calculate, which is called the transformation matrix, right? So there are actually two mechanisms for obtaining W based on our goal, based on the desired outcome and the task. And these are signal representation or classification, right? So if the goal of your feature extraction is to represent the original information in a lower dimensional space by retaining as much of the original information as possible, then you are motivated by a signal representation problem. And one of the methods that is under signal representation is principal component analysis. However, if your goal is to actually do classification, then the goal is to do feature extraction such that you make the problem of classification easier. You make the problem a lot easier to solve in this lower dimensional space. And one of the methods to do that is linear discriminant analysis. Linear discriminant analysis is also called Fisher linear discriminant, in case some of you are familiar with the other name, right? So PCA aims to learn the best data representation. However, that might not be the best class separation if your data is made up of multiple classes. And PCA is unsupervised, which means it does not look at the labels of the data. It chooses a projection that is efficient in terms of representation without taking the class labels into consideration. However, LDA aims to preserve the class separation or even improve it. So it's a supervised method that chooses the projection matrix W such that it is efficient for discrimination between classes. So let's just visualize things to make things easier to understand. If you have this data set, where you have the data set is the color represents the class. So we have a data set that has two different classes, the blue one and the red one. And this is a very high dimensional data. So we would like to reduce the dimensionality of the data. If you use PCA, what PCA would try to do is to preserve as much information as possible. So it would project it on this axis, on this vector. And we're going to explain the details later on. But that's what it would do. But as you can see, if we project the entire data on this one axis, these red classes and blue classes would be significantly overlapping. So we preserve the information in terms of the variance of the data. However, it is very hard to classify the samples now. While LDA, on the other hand, would project the data on a different vector that has a different direction, such that it maximizes the distance between classes. So as you can see, if you project the data on this vector, it is very easy to define a simple threshold here and say, well, if my sample has a value larger than the threshold, then it's one of the red samples, and if it's lower, it's one of the blue samples, right? So this is our motivation for today. Now we're going to go into details and explain how PCA works, how LDA works, and compare them. So as we said, PCA is an unsupervised feature extraction method. It is linear. The new features are going to be linear combinations of the original features. And our goal is to find the feature space with minimum loss of information. So we're going to try to minimize how much information we lose when we reduce the dimensionality of the data. And PCA finds this best subspace that captures as much of the data variance as possible, right? So to do that, we would like the new features that we learn, in order to reduce redundancy, we would like them to be linearly independent in order to ensure that we have maximum variability, right? So you can think of it like this. If we have our data, which is like this black ellipsoid, in the original space, feature space, x1 and x2, what PCA would aim to do is, would change the feature space to go to z1, z2, right? That's what it's trying to do. It's simply trying to look at the data from different angles until it finds the best way to look at the data, where we can use as few features as possible, but still understand the variance of the data. So PCA would take this data and would change the system of axes or our feature space from x1, x2 to z1, z2. It will center the data, it would rotate the axes and so on. Okay? So the underlying assumption, however, for PCA is that the most important aspect of the data lies on the projection with the greatest variance. And we will explain that in detail, right? So what PCA would do is, would transform the data to a new coordinate system, such that the feature with the greatest variance would lie on the first coordinate. And this is not really accurate, and we'll explain that later on. But basically, we will look at the variance of the data, and we want our first axis, our first principal component, to be the one with the greatest variance. And the second one will be the one with the second greatest variance, and so on, right? So if you have a data set that looks like this, what PCA would look like, you see that the greatest variance is along this vector, along this line. So the first principal component would be the red one, right? While the second greatest variance in the data is along this line. So this is where you'd have the second principal component. That is basically what PCA will do. Now, we just mentioned the algorithm, and then we're going to explain each step in detail, right? So what PCA does, it actually first calculates the covariance matrix of the data, and then it does singular value decomposition, or it calculates the eigenvalues and vectors of this covariance matrix, and then it chooses the k eigenvectors that correspond to the largest k eigenvalues, and then project the data onto this new k eigenvectors, right? So just some preliminaries. The input to our algorithm is simply data x, that where we have n samples are the features. And if you think of it, now we're going to go into a bit of a background, right? So if you look at the mean of the data does not tell us much about the data except some sort of a middle point, right? That's why we always look at variance or standard deviation, because it, along with the mean, it really gives us a lot more understanding of what the data looks like, right? So for example, if you look at these two data sets, the red and the blue one, they both have the same mean, but they really look very different from each other, right? Because of the variance. One of them has very high variance, one of them has very low variance, right? So now, the first step of the principal component we said is to calculate the covariance matrix. So we're going to do a bit of background until we explain what is covariance matrix and why do we need it and why is it useful, right? So the first thing to do is, I'm just going to do a bit of basic expected random. What is a random variable? A random variable, you can, I'm not going to do the stats part or the probabilities part, but just think of each feature in our data could be a random variable, right? So the expected value of a random variable is actually, could be used, you could replace that with the mean, right? So if you have one of your features and you would like to calculate the expected value, one way to do it is simply to go look at each one of the values that this feature takes and how many times it happens, which is the frequency, and then you can calculate the expected value. Well, you can simply calculate the sample mean, which is simply you go over all your samples and you calculate their mean. And the mean is actually an unbiased estimator of the expected value. This is something we discussed in our first talk last term. So we can go over it in the end of the talk if you would like to discuss what's an unbiased estimate of something, right? But simply what we're saying is, you have the data, the first thing you can do is find the mean. for a given feature. The second thing you can do is actually measure the variance of that feature, which is going to tell you how spread out is this feature. And to calculate the variance is very simple. First, you calculate the mean, then you measure the square distance between each sample to the mean. And you sum that across all the samples, and you divide by 1n minus 1. And the reason we divide by 1n minus 1 instead of 1 over n is also to get an unbiased estimator of the variance, right? So now, the mean and variance are actually one-dimensional measures, which means they are useful when you look at one feature. So you can go take any feature in your data, and you look at the mean and the variance to understand how that feature is behaving. But also, what is very interesting is to understand how features interact with each other. So it is very useful to find out how much features vary from the mean with respect to each other, right? So that is called covariance, okay? So the covariance between two different features is actually going to measure, quantify a linear relationship between how these two features change with each other. Now, to calculate the covariance, it looks a lot like the variance. Basically, you take two features and you measure the distance between one feature to the mean of that feature and the other feature its distance to its corresponding mean, and you do that across all the samples and you divide by 1 over minus n. And it's obvious if you use the same feature, xi here, you'd end up with the variance, right? So what is the covariance here, just to get an intuition? The covariance tells us multiple things. The sign of the covariance, being positive or negative, will indicate how two variables change together. So if you have a positive sign, then both of these random variables will increase together. So if one of them increases, the other one increases as well. If the covariance has a negative sign, then when one of them increases, the other one will decrease, right? And if the covariance is 0, it means these two random variables or these two features do not have a linear relationship. They're independent of each other, right? So if you look at these examples, if you think of each x-axis has one feature and the y-axis has another feature. So these two features, there is a very clear covariance, positive covariance between them, right? They're linearly proportional. As one of them increases, the other one increases as well. That's why the covariance is very positive, very large positive value. And if you look at the second example, the green one, you can see that there is a negative correlation, negative covariance between them. While if you look at the other two samples, you can't really say anything, right? So in this case, you have a value very close to 0 because they don't look like they have any kind of relationship between each other. And in this case, you can't really say anything because in here there is a positive covariance, and in this part there is negative covariance, right? So covariance, then we can define something called the covariance matrix. And the covariance matrix is simply, you take each pair of features you have and you measure the covariance between them. And the covariance matrix, once you have calculated that for all the pairs, the advantage is you would understand how each pair of features interact with each other. And since you're trying to reduce the dimensionality without losing information, you can easily think and see that, well, if I have two features that are that there is a very large correlation between them or covariance between them, then I can simply use only one of them and drop the other one. Because if I know one, I can easily predict the other one, right? So that is the underlying assumption or idea behind PCA, right? So you calculate the covariance matrix to measure how each pair of features change with respect to each other, right? So once you do that, so you can easily see like, okay, we take feature 1 with itself, then feature 1 with feature 2, and so on until feature 1 with feature n, right? And actually this should be d because we said we have d many features. And you do the same everywhere. And you can easily see that this is actually a symmetric matrix. So the covariance between feature 1 and feature 2 is the same as the covariance between feature 2 and feature 1. So this sigma covariance matrix is symmetric and it is positive semi-definite. A positive semi-definite matrix is simply a matrix that has all its eigenvalues are going to be positive, right? And we're going to go into what's an eigenvalue in a bit, right? So let's just focus on the covariance bit, right? So PCA aims to re-express the data, re-represent the data as a linear combination of its basis vectors. So if we take the original data and x, and we have the new transform data. And if you look at, if you carefully look at it, you notice here, we're not trying to reduce the dimensionality yet. We're just trying to change the expression of the data or project the data and change how it looks, and then we will reduce the dimensionality. Because the x and z have the same dimensionality, and our transformation matrix P is dimensionality d by d, right? So the equation to change the system of coordinates or to change the basis is simply z equals P of x. And P is simply going to be a rotation and a stretching matrix. The rows of P are going to be the new basis vectors, are the new coordinate system we have, right? And we would like these vectors to be uncorrelated, right? And these D projections are the eigenvectors of the covariance matrix, right? So let's first just define what's an eigenvector, right? So the definition is vector x is called an eigenvector of matrix A if there is a value, lambda, that is not equal to 0, such that if you multiply x with the matrix A, is going to be equal to lambda multiplied by x. And we call lambda an eigenvalue of matrix A, and we call x an eigenvector of matrix A, right? So the eigenvectors of a matrix correspond to different distinct eigenvalues, and they are independent of each other, right? So if you have eigenvectors that correspond to different eigenvalues, then they're linearly independent, which means they are good. They could be used as our new basis vector. And the one interpretation for the eigenvalue and eigenvector thing is, well, transformation A does not change the direction of the vector, it just changed its scale. So to understand what's an eigenvalue or eigenvector is, well, we have this matrix A, which if we multiply it with this vector, the direction of this vector will not change, right? It will only change its scale, right? So if we look at the row vectors of this transformation matrix, they will become our new principal component, right? And now we'll explain that. We'll explain why this is the case. Well, we have matrix X, and we're trying to find a good way to re-express it. And to do that, we're trying to find a good matrix, transformation matrix P. Now, to calculate the covariance of a matrix X, we can do that by multiplying X with itself and dividing by 1n minus 1, right? So since our goal is to reduce the redundancy in the new data, we would like each variable to covary as little as possible with each other in the new transformed data Z. So in order to remove this redundancy, we would like the covariances between the separate measurements to be 0, but not in X, but in Z, right? So we can calculate as the covariance matrix of X and the covariance matrix of Z, and we would like the covariance matrix of Z to be diagonal, right? So, and the reason for that is, if all the terms that are off the diagonal are 0, it means all the new features covary with each other as little as possible, right? So in order to solve PCA, we have to find the eigenvectors of the covariance matrix, right? And we're going to prove that. We're going to do the derivation in 1 or 2 slides, right? So if we have original data X and we have transformed data Z, where Z equals P of X, we can easily calculate S of X. And we would like transformation matrix P to give us Z such that the covariance matrix S of Z is going to be diagonalized, right? And the P that gives us this diagonalized covariance matrix is going to be where the rows are the principal components, not of X, I'm sorry, of the covariance matrix. Now let's see why that's the case, right? So let's go back to our goal. We would like this covariance matrix to be diagonal, which means we want all the off diagonal terms to be 0, because that would mean our features are linearly independent of each other. Now, by definition, S of Z is 1 over n minus 1 Z multiplied with itself transposed, right? But we know Z equals P of X. So we plug in P of X in both sides, right? Now, you can take this transpose. So if you have two matrices multiplied with each other and you do the transpose, you can simply just reverse the matrix multiplication and you transpose each one of them, right? This is just matrix multiplication properties. So once you've done that, you can see that you have X multiplied with XT. All right, so we can call that matrix A. And this matrix A is multiplied both from the left and the right with the transformation matrix P. Now we would like this whole term, PA, P transpose, to be diagonal, because that's what we would like. So we would like this matrix P, when we multiply it with A, to turn A into a diagonalized matrix, right? Now, a symmetric matrix A, because we know that this is symmetric, and when you multiply any matrix with its transpose self, you're going to end up with a symmetric matrix. So symmetric matrix A is diagonalized by orthogonal matrices. And orthogonal matrices are simply matrices which their columns are linearly independent, which means orthogonal to each other, right? So we know that a symmetric matrix A can be diagonalized by multiplying it by E of t, right? Where D is a diagonal matrix that has the eigenvalues of A, and E and E of t are actually the matrix of eigenvectors of A arranged as columns in E and arranged as row in E of E to the t, right? So we would like to select matrix P such that when we would like to select it such that it diagonalizes X multiplied with itself, X, xt, right? So if we say P is equal to E of t, which means we equal our transformation matrix to the eigenvectors of the covariance matrix, and then we know that the covariance matrix can be diagonalized by multiplying with the eigenvectors, with the eigenvalues, and the eigenvectors again. And because we know that this E of t, right, this matrix, the matrix of eigenvectors, we know it's orthogonal. So from matrix property, the inverse and the transpose of an orthogonal matrix are equal to each other, right? So let's go back where we left off, right? We have the covariance matrix of transformed data equals P, A, P to the T, right? But now we just said that A actually equals P, D, P, right? Which means we can multiply P with P to the T and P with P to the T. But we know that the transpose is also equal to the inverse, which means multiplying P with its transpose is going to give us the identity matrix. And the same on the right-hand side, multiplying P with its transpose is equivalent to multiplying it with its inverse, which means it's going to give us identity. And that would leave us only with matrix D, which is a diagonal matrix of the eigenvalues, right? And that shows us is if you would like the covariance matrix of your transformed data to have independent features, then you should select the transformation matrix to be equal to the eigenvectors of the covariance of the original data, right? So that is the first step of the principal component analysis, which is calculate the covariance matrix, and then calculate its eigenvectors and eigenvalues, and that would be equal. And you can use that to build the transformation matrix. Now, the last step is after we have transformed the data into a new dimensional space where each pair of features are independent of each other, linearly independent, then now we can select the k dimensions, the k features that correspond to the largest eigenvalues because they correspond to the largest variance of the data, right? So the question is, well, how do I choose k? What is the best number of components that I can use? Well, there is no correct answer, and there is multiple ways to do that, right? But one way is to simply look at the eigenvalues and aggregate them to calculate something called proportion of variance. And that means is, well, what is the proportion of variance that is explained by the first k features, the first 5 features, first 6 features, right? So what you do is you have in the denominator is the summation of all your eigenvalues. And in the denominator, you order these eigenvalues in descending order. And you keep adding the first 2, the first 3, 4, 5, 6, and so on, until your proportion of variance is large enough based on your application, right? So sometimes we can use this value to be larger than 0.9. Or other methods is that you can actually plot this POV versus K. So you can actually see what's the POV, how this variance, proportion of variance preserved by the new transformed data as you change K. And you stop once you reach an elbow. And we're going to show you an example here, right? And the proportion of variance explained by each one of the principal components is simply its eigenvalue divided by the summation of all the eigenvalues, right? So if you have this example data where we have all these data samples in this three-dimensional space where each axis is one of the genes, well, PCA would simply project the data into these two, PC1 and PC2, the first principal component and the second principal component. And we'll get rid of the third one because it has negligible eigenvalue. And once we project that from 3D to 2D, the data would look something like that, right? And one way to choose the number of dimensions, if you have very high dimensional data and you're not sure how many, what is the value of K, how many dimensions should you keep? Well, you can simply plot these principal components, and as you add, you can see the proportion of variance explained by the first principal component, the second one, the third one, and so on. And you can see that it goes down. So you can simply, well, if I am interested in preserving, let's say 80%, well, this one gives me 22, this one gives me 18, and so on. So you keep adding them up, you keep increasing the number of dimensions until you have preserved enough variance in your transformed data, right? So before I discuss the assumptions and limits, let me see if there are any questions. Okay, right. So the assumptions and limits of PCA, right? So the obvious and the first limit of PCA is that it's a linear method, right? So it's doing a linear transformation. So if there are nonlinear relationships between your features, then PCA will not be able to detect them. This can actually be alleviated by using kernel PCA in order to be able to detect nonlinear relationships between the features. But the other limit is that PCA, as you can see, it uses the mean and the variance and the covariance. And the mean and the variance are actually sufficient statistics because they can completely describe the probability distribution, but as long as that probability distribution is Gaussian. So if you don't have a Gaussian distribution of your data, then PCA is not going to give optimal performance. It's not going to give you optimal results. However, the reason that making the Gaussian assumption is not such it's a very good assumption is because it guarantees that the signal to noise ratio and the covariance matrix will fully characterize the noise and the redundancies in the data, right? So as we said before, when you saw how PCA works, it does not take the class information into consideration, which means there is absolutely no guarantee that the classes in this transformed data will be better separated than the original data. So PCA is really equivalent of walking around the data and trying to find a good angle to look at the data where you can use as few features as possible and still understand the variance of the data, right? So it really, like, PCA is simply trying to pose the question is that I have this data in some basis vector, and I'm trying to find another basis vector, which is a linear combination of the original basis vectors, but can better represent the data, can better express the data, right? So PCA will allow us to do this dimensionality reduction by simply discarding the components that have very small eigenvalues, right? So the main applications for PCA is to do noise reduction, to do data visualization, and to do data compression. And it can also be useful as a pre-processing step by reducing the computational complexity of the model, right? But you should be careful because if the direction of greatest variance is not the most informative one, then PCA is not a very good idea, right? So just simply PCA will take a data in this original basis vector, and as you can see the data here, and it will project it and change it to this new basis vector, right? So let's have an example for how PCA does compression. How can we compress data using PCA, right? Well, simply, let's say you have a data, you have some image, and you divide it into patches, where each patch contains 12 by 12 pixels on a grid, right? Which means each patch has 144 pixels. If you think of each patch in an image as simply a vector of 144 dimensions, well, we can now reduce the number of dimensions, which means reduce the number of pixels in each batch using PCA to try to compress the data while preserving as much information as possible, right? So if this is the original image where we're not doing any compression, if you divide it into this aforementioned patches, and then you compress the data from having each batch represented by 144 dimensions to 60, you will have this new image. And as you can see, the difference is not that big. You can see a difference in the contrast, but it's still a very good image. And you reduce the dimensionality by over half. You can further reduce the dimensionality from 144 to 16, and the image still looks good, right? You can even reduce the dimensionality from 144 to 6, and you can get a very blurry image. But keep in mind, this image is a very low resolution image, but it's also doesn't use a lot of data, right? You can easily store this somewhere, right? You can even reduce it from 144 to 3D, which means each batch that originally had 144 pixels, right now only has 3 pixels. And the image still looks very good. Well, not very good, very blurry actually, but it's still, in terms of preserving as much variance, is good enough. But one of the main limits of PCA is it cannot really capture nonlinear structures. So if your data originally looked like this, PCA will not be able to capture this structure when it tries to project the data into lower dimension. Also, because PCA does not know and does not observe the class labels, if you have a data set where you have this is one class and this is one class, PCA will project them into these axes to preserve as much variance as possible. But you will not be able to distinguish the two classes anymore. And this is one of the main limits of PCA, right? So now this actually, this is the main motivation for the second method we will talk about, which is called linear discriminant analysis. And PCA finds the minimum number of components that best represents the data. But it does not guarantee at all that this new transformed data is going to be any useful for our classification path. So we want a new method that will reduce the dimensionality under some constraint of maximizing the class discrimination, right? So the best way to actually maximize the discrimination between two different classes is to increase the interclass distances and reduce the intra-class distances. Simply saying, I want the points that belong to the same class to be very tightly packed, and I want them to be very far away, well separated from the points of the other classes, right? So to calculate, to quantify this interclass and intra-class distances, we're going to introduce new matrices called between and within class scatter matrices, right? So simply is, if we have this data where we have the blue and the red represent different classes, if you project them on W1, you will have significant overlap between the two classes. While if you project the same data on W2, you're going to have really good class separation. And that is the main motivation of LDA, right? So before LDA, we might have a data set that looks like this. We want it to look something like this after LDA. We really want to not just reduce the dimensionality, but to improve the class separation after we have transformed the data, right? So LDA is still a linear method, which means the transformed data is a result of multiplying the original data with a matrix, a transformation matrix W, right? So how do we know ahead of time that this transformed data will be good in terms of class separation? Well, to do that, we need to define a criterion, a separability criterion that increases as we increase the separability, right? So first thing first, let's look at the projected means of the data. Well, if you have data X and you sum over all the samples that belong to a given class, you will get the mean of class I, right? Well, if you do the same in the projected data and the transformed data, you will end up with the mean of the transformed samples belonging to class I. But this also can be calculated, right? Either you do it through the definition, but Z is actually equal to WX, then this is simply the projected mean is the original mean multiplied by the transformation matrix. So we would like to measure the distance between them. So the distance between, if we have two classes only, this is the projected mean of the class 2, and this is the projected mean of class 1. We want to measure the distance. And the larger the distance, the better the separation between the classes, and it means we have a better projection. And we know that this mu2 and mu1, tilde mu2 and tilde mu1, are simply W, the transformation matrix, multiplied by mu1 and mu2, their difference, right? And this is our objective function that we're trying to maximize because we want to maximize class separation, right? But this distance between the mean does not actually take the variance into consideration. So if we want the means to be well separated with respect to the variances, we simply normalize the objective function with respect to the within class variance, right? So simply you calculate for each one of the sample the distance between the data samples and its projected mean. And you do the same for class 1 and class 2, and you divide our original objective function with that. So now the new objective function is trying to maximize the distance between the means, normalized with respect to the within class variance, right? So because you can see here we have, if this was our data and we were only trying to maximize the distance between the mean, we would be able to project the data here because this would maximize the distance between the means, but it would not maximize the distance with respect to the variance, right? So after normalizing our objective function with respect to the variance, this would be our ideal projection because you can see the distance between the mean is large with respect to the variance, right? So now let's define the matrices we need and let's see how we can calculate our transformation matrix, how we can find our ideal transformation matrix, right? So we define scatter for class I. It's a measure of the variance in class I. And the total within class scatter is you calculate the within class scatter for class 1 and within class scatter for class 2, right? So now we want to find J, our objective function, as an explicit function of W, right? So we define the scatter matrices as follows, right? So the scatter matrix in the original data for class I is simply the distance between the samples and the mean of class I, right? Squared, so we multiply with the sum. Now, the total within class scatter for the original data is the scatter matrix for data 1 plus the scatter data for original. For data 2, simply we add another summation over all the classes, right? And this is the within class scatter matrix. The between class scatter matrix is simply going to be the distance between the means, the distance between the mean of class 1 and the distance between the mean of class 2. That's going to be called SV, right? So the between class scatter matrix SP is the distance between mu1 and mu2, which are the means of each class of the data in the original space, right? If you remember our objective function in the denominator, we had this tilde mu2 minus tilde mu1, which is the projected mean rather than the original mean. But the projected mean is simply the transformation matrix multiplied with the mean, and here the transformation matrix multiplied with the mean, and this is squared because we're taking the second one, right? So then we can easily take these W's out and rewrite it as the transformation matrix multiplied with the between class scatter of the original data, between class scatter matrix of the original data, multiplied with the transformation matrix from both sides. So now let's do the same for the within class variance. Well, that was what we calculated before as the within class scatter matrix. Well, but we, in the denominator of our objective function, we divided by the scatter of the projected data, right? So the scatter of the projected data is the distance between the projected data and the projected mean, and that is simply the projected data is the transformation matrix multiplied with the original data, and the projected mean is the transformation matrix multiplied with the original mean, with the mean of the data for class I. And that can be rewritten as the distance between X and the mean of that class multiplied from both left and right with the transformation matrix. But this thing, this whole term, is simply the scatter matrix for class I in the original data. So we can write the scatter of the projected data in terms of the transformation matrix and the scatter of the original data. And since this was the denominator of our objective function, we just do the same, we add it up, and we end up with W, S of W, W, right? So now you can clearly see how we rewrote our original objective function in terms of W and the between class scatter matrices and the within class scatter matrix, right? In order to find the optimal W that will maximize this function, simply take the derivative with respect to W, equate it to 0, and then isolate it on one side and find W that maximizes this function. And this is going to be the answer. But we're going to do the derivation right now, right? So this is our original objective function. We want to maximize it, so you take the derivative with respect to W, right? So first take it with respect to, take the derivative of the denominator, and that is going to be 2SPW, right? Because first you take the derivative from the left, the derivative from the right, and they're going to be equal to each other, and you add them up. And the denominator does not change. And then you do minus And then now we're going to take the derivative with respect to the denominator. So we square the denominator right here, and then we take the derivative from the left and from the right, and we end up with this term. And the denominator does not change. So to find the optimal W, which we call it W star, we equate this to 0, which means it is equating this to 0. So we have two terms. We can take one of them to the other side, and we have this term equals to this term. And what we can do is we can cancel the denominator from here with the denominator from here, and you end up with this denominator only. And then you can rewrite this and call it lambda. And then the equation would look like it's 2 SB W star minus lambda, which is this whole thing, 2 S of W, W star, and this is equal to 0. So you simply now isolate W star, and you end up with a solution, which is the inverse of the within class scatter matrix multiplied with the distance between the means, right? So we solved LDA for a two-class classification problem. But what if you have a C-class problem, C-class classification problem? What if your data have more than two classes? Now, LDA can reduce the dimensionality from D dimensions to C minus 1 dimensions, right? By using C minus 1 projection vectors. But the main assumption is the number of classes is smaller than the number of dimensions, right? So now we're going to do the exact same thing before, but we're going to generalize by, instead of having two classes, we have more, right? So the dimensionality of our input to the algorithm will be simply X, which is the data where we have N samples, D features, and this has C classes. And this is our transformation matrix. That's going to be D C minus 1, where this is the number of classes, and Z has C minus 1 dimensionality and N many samples, right? So now, if you want to calculate the within class scatter matrix, the total, which means across all classes, well, you calculate the scatter matrix for each class by measuring its distance of the samples that belong to that class with the mean of that class. And then you sum, instead of doing from 1 to 2, you're summing from 1 to C, where C is the number of classes, right? As for between classes scatter, this is slightly different. So in the case of between classes scatter, what we're going to measure the distance between is the mean of feature I, right? I'm sorry, the mean of samples that belong to class I with the distance of the mean of the whole data. And then we multiply with Ni, which is the number of instances that belong to class I, which means now we have two means. We have the mean of the entire data and the mean of the class. And we want the distance of the mean of the data to be as far away from possible as, the mean of the class to be as far away from possible as the mean of the data. And the total scatter is going to be equal to the within class and the between class scatter, right? So in the transformed space, these matrices will look something like this. So the within class scatter matrix is going to be the distance between the new data, the projected data, transformed data, and the projected means, which can be rewritten in terms of W and SW like this, which we've done before. And the between class scatter matrix tilde SP is going to be the distance between the projected mean of samples belonging to this class and the original mean, right? And that's going to be WSPW, right? Now, LDA will try to find a transformation that will maximize the following criterion function, right? So as you can see, we have here the between class scatter matrix divided by the within class, because we want to maximize the between class scatter while minimizing the within class scatter. And we have rewritten these in terms of W, the transformation matrix, and the scatter matrices of the original data, right? So these represent the determinant of matrices. So solving this problem is slightly more complicated than solving it in the case of two classes, right? So to solve this problem, you have to do something called, you have to find the generalized eigenvectors corresponding to the largest eigenvalues of this matrix, right? So if you come here, if you take the derivative, you equate it to 0 and you isolate the terms, you end up with a problem where you're required to find the generalized eigenvectors. And not to go into too much details, but the generalized eigenvectors are different from the original finding the eigenvalues and eigenvector in the sense that you don't have to have, some of the eigenvalues could be equal to 0 in that case. So it's a more relaxed version of finding the eigenvalues and eigenvectors, right? So the generalized eigenvalue problem can be solved by first computing the eigenvalues, which are roots to the following characteristic polynomial. So I took this matrix, you do minus lambda I is W, and you have this characteristic polynomial. You have to find its roots, and these are going to be the eigenvalues that are going to be used to solve the generalized eigenvalue problem. And once you've done that, then you can solve this problem to find the ideal W, right? And as you can see here, this is a discriminant operator. This process will generate the eigenvalues and the eigenvectors. However, only C minus one of them should end up being non-zero, right? And the dimensionality after the projection will be C minus one at most. And for really high dimensional data, where the number of dimensions is a lot larger than the number of classes, the information represented in this C minus one dimension may not be adequate, right? So just to summarize, in the case of LDA, if you have C classes, you're going to end up with C minus one basis vectors, and you're going to project the data from D space to C minus one space. And now you see the difference between LDA and PCA, because in PCA, you get to choose the number of features. You get to choose K. You can increase K or reduce it, but in LDA, that's not something you get to choose. And in LDA, we're trying to maximize the between classes scatter to within class scatter ratio for best separability. However, just like we talked about the limits of PCA, we really have also a lot of limits for LDA. So LDA assumes that the class distributions are unimodal or they're Gaussian. So for example, if you look at this case, we have two classes that represent, each one of them is represented by a circle. Now, the means of both classes and the mean of the entire data are equal to each other. So to try to do the separation is going to be very tricky. And if the original data looks something like this, right? If the data does not have this Gaussian shapes or unimodal shapes, LDA will fail and will not give you good results. If the data is highly overlapping, if the data is multimodal, LDA will be of little use, right? And there is actually an interesting case in which LDA will fail if the discriminatory information actually lies in the variance rather than the mean, right? So if you, and PCA will prevail. So if you look at, this is our original data. The blue and the red represent different classes. LDA will try to project these two data sets, these two classes, to maximize the distance between the means, and you will end up with this data on the LDA basis vector, where it's very hard to separate this data. It's very hard to separate the two classes. However, PCA will try to project the data to maximize the variance, and you will end up with this projected data, where it's much easier to actually separate the two classes, right? So just a few examples to wrap up. If our original data looked like this and we had two classes, PCA will project the data to look like this, while LDA will project the data to have a much better class separation. PCA is gonna project the data, transform the data, where the new basis vectors, lambda 1, lambda 2, maximize the variance, which means preserve as much information as possible, while LDA will try to project the data in order to maximize the class separation, right? To summarize, we talked today about linear feature extraction methods for dimensionality reduction. And we discussed two methods in detail: PCA, which is unsupervised and try to preserve as much information as possible when reducing the dimensionality of the data. LDA, on the other hand, is supervised and try to improve or preserve the class separation in the new projected data. So I would like to thank our sponsors, CPA and Ontario, on the end. And now we can have a discussion. Anybody has any questions or anything to discuss, can do that. I'm going to close the full screen mode to be able to monitor the chat.
Okay.
Yeah, we have a lot of formulas, unfortunately, because I was not sure the background. I wanted to cover the topic regardless of the background of the audience.
There was a lot of formulas. It was interesting topics, though, that's for sure.
Yeah.
Mm-hmm.
If not many people are available, maybe you can switch to our Discord if some people would like to have a discussion.
Sure, we can do that.
Cool.
Yeah, so I put the Discord link in the Twitch chat if anyone would like to join, but that's going to be it for us today. So thank you everyone for attending, and again, thank you CPA Ontario for sponsoring CAIS. Have a great day, everyone.
You too. Thank you, everyone.